Let's proceed with disjoint cycles. Before this, we have learned on cycles. Cycle, which is a permutation in a metric form that can be written in much simpler notation. What about disjoint cycle? Disjoint cycle is actually any integer is moved by at most one. Okay, at most one of this cycle. Thus, one number appears in the notation of two different cycles. We can say in example 3, number 1, this is example for disjoint cycles. We can find in first cycle here, only one number appears only one. 1, 3, 6, 2 to x, 4 to 7, 7 to 5. For joint cycles, it can be appears more than 1. 1 to 2, and the second one we have 3 is mapped to 2. This one also we have 1 maps to 3, 3 maps to 5, 5 maps to 6. The second one we have 2 maps to 4, 4 to 6. 6 appears 2 times here. And for this one also disjoint cycles, when we have 1 is mapped to 6, the second one we have 2 is mapped to 4, 4 is mapped to 7, 7 is mapped to 5, and this one 3 is mapped to 8. Both of these are disjoint cycle, and this one are disjoint cycles. Theorem 1 and 2 is about the permutation of disjoint cycles. Theorem 1, every permutation sigma of a finite set is a product of disjoint cycle. When we multiply disjoint cycle, we will obtain permutation sigma. Also, for theorem number 2, the multiplication of disjoint cycle is commutative. Let's see some example. Example number 4. Number 1, we consider the cycles 1, 4, 5, and 6, and also 2, 3 in symmetric group degree 6. If we multiply these two cycles, that means 2, 3 multiply with 1, 4, 5, 6, it is also equal when we multiply 1, 4, 5, 6 with the cycle of 2, 3. That means they are commutative. The multiplication of these two cycles is commutative. Number 2, consider cycle 1, 4, 5, 6, and also the cycle of 2, 1, 5 in symmetric group degree 8. Then we multiply, we find that this cycle, this is actually a joint cycle because we have 5 here and then we have 5 here. Multiplying of this, we find that 1, 4, 5, 6 multiply with 2, 1, 5, or we write it in metric notation. We obtain 1 to 5, and then 5 goes to 6. So we have 6 here. 6 to 6, 6 go back to 1. In total, we have 1, 6. That means 1 to 6, 6 go to 1. For a second cycle, we have 2 to 1, 1 to 4, 4 to 4, and then 4 to 5. 5 to 2, 2 to 2. That means we have 2 to 4, and then 4 to 5. 2 to 4, 4 to 5. Either we want to write in this or in this cycle notation. If we multiply this joint cycle, we start on the left hand side, which is 2, 1, 5, and then multiply with 1, 4, 5, 6. We will obtain 1, 4, 2, and the second cycle is 5, 6. Okay, neither this permutation is a cycle. Definition 4 is about the order of permutation. The order of permutation alpha, which is the smallest positive integer n, such that when we have alpha here is a permutation, and then alpha to the power of n, which is equal to identity. When we multiply alpha with alpha, alpha with another alpha, and we obtain identity, then that is the order of that permutation, and denoted by this. Now, based on Theorem 3, a permutation of cycle with length n has order n. We can find it in example 5. For example, we have A1, A2. Okay, cycle of A1, A2, which means the order of this is 2. A1, A2, A3, the order of this cycle is 3. So let gamma be 1, 4, 6. Then we have here, this is example, and then for gamma 146, cycle of 146, we have order of gamma is 1, 2, 3. That means 3. And then we multiply gamma with gamma. 146 multiply with 146, and what we have here is 164. 1 goes to 4, 4 goes to 6, 6 to 1, 1 to 4. We have 164, which is order 3. We multiply again gamma cube, and this is also equal to gamma times gamma 2, gamma multiply with gamma 2, or gamma times gamma times gamma. We obtain gamma cube here, gamma power 3, which is 164 multiplied with 146. What we have here, 1, 4, and 6, which is identity. Then since we have identity here, that means this is the order of power 3. I mean the order of this gamma is 3. 1, 2, 3. Because we have gamma times gamma square times gamma cube. Up to gamma cube, we obtain identity. That means this is the order, give the order of this cycle of permutation, 1, 2, 3.